A second method of understanding the degree of correlation is again a graphical method. It is called a correlation graph. What you do in this, you have data with respect to two variables x and y. You draw the correlation graph. This is especially useful when you have time series data. So if you have the two variables x and y, calculate the mean value of x and the mean value of y. Choose your axis such that the parallel lines corresponding to x bar and y bar, okay, it's supposed to be okay, let me try that again. Choose your units of the axis such that the parallel lines representing the two average values are as close to each other as possible. And now plot. Here you have time. Sorry, let me do that again. You have your time. Again, I'm drawing this for a time series data. So say you have January, February, March, April, May, June, and so on. And over here, you are on the y-axis, you are plotting both x and y values. So the solid line corresponds to x, and the dotted line corresponds to y. Okay, let me try that again. 1 second. Maybe I should. Okay, this is the best that I could do. I'm sure you can do much better with a proper pencil and on paper. So the dotted line shows the observations of the y values or the series y. Now, as you can see, the movement in this particular example that I have drawn, the movement of both x and y are almost always in the same direction. So when the x series is increasing, the y series is also increasing. When the y series is reducing, the x series is also falling. So when you have movement, such co-movement being seen, you can conclude that there is a high degree of correlation. So this would be an example of a high degree of positive correlation. You might even have a case of negative correlation, where when your x series, when it is increasing, if you observe that the y series is decreasing and so on, in that case you are looking at a correlation graph that exhibits negative correlation. I can just show you roughly. Again, a correlation graph depicting negative correlation. So the solid line represents x bar, dotted line representing y bar, and say your x series is approximately like that, and say your y series is on the other hand. Remember, the correlation need not be exact, but as you can see here, the dotted line is increasing when the solid line is decreasing. So here this would be an example of a negative correlation. Once again, the correlation graph is also very popular because it gives you a visual idea of the degree of association between the two variables. Correlation graphs are used generally and most popularly used for time series data. So talking about share values of different stock market or share markets of companies. Okay, price changes, trends in prices, say prices of gold versus prices of maybe necessary goods, prices of petroleum versus inflation, and so on. All these variables, because these are time series data that you're talking about, they are very easy to understand and very visually appealing when you represent it in using the correlation graph. But like I was saying, the main demerit of this graphical method is the same as the earlier scatter plot that I was talking about. The main demerit is that it does not give you an exact value that gives a measure of the degree of association. The maximum that it can tell you is whether it is positively correlated or negatively correlated, but it can't tell you whether the degree of correlation is 0.97 or whether the degree of correlation is something as small as 0.34. So to do that, to get a number or a value that indicates the degree of association, you need to use the third popular method, which is the Karl-Pearson's coefficient of correlation. Karl-Pearson's correlation coefficient or coefficient of correlation. Okay. The coefficient of correlation, as mentioned by Karl-Pearson, generally it is denoted by R. The formula is the covariance of x comma y divided by the standard deviation of x and the standard deviation of y. That is, it is pxy by sigma x sigma y. Now, what is covariance of x and y? Covariance between variables x and y, denoted here as p subscript xy, will be 1 by n times summation x minus x bar into y minus y bar. I hope you remember what the standard deviation formula is. Standard deviation formula is root under the mean of, sorry, I should stick to capital. One second. Standard deviation is the mean of deviations from mean whole squared, right? And standard deviation of y is root under summation y minus y bar whole square divided by n. Another name for the Karl-Pearson's correlation coefficient is the product moment correlation coefficient or linear correlation coefficient. Now, several books, they use small x or the small letter to symbolize, to represent deviations from the mean. So small y will represent y minus y bar. So if you're using these symbols, you can actually write your R can be written as summation small x small y divided by n times sigma x sigma y or summation xy divided by root under summation x square summation small y square. Now these are all the same formulas. One can be derived from the other. Okay, since you don't have derivation in your syllabus, I'm not going to bother going into that. So they are all one and the same. Okay, so this is the same thing as this, which is the same thing as the ratio of covariance of the two variables to the product of their standard deviations. Okay, the values of R will vary between -1 and 1. So your value of R will range from -1 to +1, where R equals to -1 means perfectly negative correlation. R equals to +1 means perfect positive correlation. And R equals to 0 means no correlation whatsoever. Now remember, the Karl Pearson's coefficient of correlation measures linear correlation alone. So R equals to -1 means perfectly negative linear correlation. R equals to +1 means perfectly positive linear correlation, and R equal to 0 means no linear correlation. This is I don't think they have discussed the merits and demerits of the Karl Pearson's method. Have a look at an example where we are calculating the Karl Pearson's correlation coefficient for bivariate data. We have two variables x and y, and we have these observations relating to x and y. The Karl Pearson's correlation coefficient formula, if you remember, was summation small x small y, where remember the small letter represents deviation from mean. So small x is x minus x bar, small y is y minus y bar, divided by root under summation x square, that is square, and square, and root under summation y square. So now we need to find all those columns that we need to calculate these values in the numerator and denominator. So basically small x is nothing but every observation xi minus x bar. Remember xi indicates the ith observation of x. Similarly, small y is yi minus y bar, where yi indicates the ith observation of y. The book that you are following, it's simply calling it capital X and capital Y. Means one and the same thing. Giving the subscript I is more technically correct, but you will get marks whichever way you write. So we need to first find the values x bar and y bar. So we know that x bar is equal to summation x divided by n, and total sum of x comes up to be 240. So your x bar is 240 divided by n is number of observations is 8, so 30. Similarly, y bar is summation y divided by n. The total value of y is 200. So your y bar will be 200 by 8, which is 25. So to find small x, that is xi minus x bar is 30. 22 minus 30 minus 8. 26 minus 30 minus 4. 29 minus 30 minus 1. 30 minus 30 0. 1, 3, 4, 5. So those are your deviations from mean of x. Similarly, yi minus y bar, instead of y bar I'll just write its value, which we calculated as 25. So I'm looking at this column and subtracting 25 from it. So 19 minus 25 is minus 6, 21 minus 25 is minus 4, 22 minus 25 minus 3, 29 minus 25 4, 2 minus 1, 2, 31 minus 25 is 6. Now we need to find xy, x square and y square. So small x square will be 64, 16, 1, 0, 1, 9, 16, 25. Small y square, that is yi minus y bar whole square, will be 36, 16, 9, 16, 4, 1, 4, 36. And you also need to find xy, summation xy. So x into y will be this column into this column, which will be minus 8 into minus 6 is positive 48, positive 16, positive 3, 0, 2, negative 3, 8 and 30, positive 30. Right? Summation x square adds up to 132. Summation y square adds up to 122. Summation xy adds up to 104. So putting all these values into your formula, you can get r as 104 divided by 132 into 122, sorry, root under 132 into root under 122. Use your calculator. 0.8195. Remember, the closer your value of r is towards 1, the higher degree of correlation it implies. So 0.8195, since the figure is positive, that means it's positive correlation, and definitely quite high correlation, positive correlation between the values of x and y.